Okay, we're back. Let's talk some waves. So today we're gonna be doing a little bit of new stuff. So we got some waves here. We got the wave. Um, we're gonna be talking about a little bit different types of waves. So quick reminder as to what we've already talked about. So we have classified waves already, but where we are going to move into the way that we classified them in the past isn't enough. While it is a great way, and we are going to still classify waves in the way of how is the medium vibrating, we are also going to expand as to um, some new ways of classifying waves. So this is stuff that you've already seen. We already have seen all of this in class. One way that we classify waves is how the medium is vibrating, and if the medium is vibrating in the same direction as the velocity or the same direction that the wave is traveling, we call that longitudinal or a compression wave. And if the wave is vibrating perpendicular to the way that it's moving, we have a transverse wave. And I'm kind of blocking it a little bit. I'm sorry for that, but this should all be review at this point. Longitudinal, parallel, transverse, perpendicular. And this is the direction that the medium is vibrating as compared to the velocity of the wave or the direction of the wave. Okay, so if we classify waves by one, how is the medium vibrating? The other way that we classify waves is what is vibrating. So what is actually vibrating? Now this is a little weird to think, but when we're looking at waves, we have already talked about how sound waves don't travel through a vacuum, right? We can't hear the sun. There is no sound that can be transmitted in outer space because there is no air, there is no medium, and if there is no medium, sound waves can't travel through that, and so we call those waves sound waves fit under the umbrella of mechanical waves. So mechanical waves require a medium to travel through. So they are actually vibrating the medium. If you are underwater and you are talking, you are actually vibrating those water molecules. If you are in air, like a normal conversation, I am vibrating those air molecules, and those vibrations travel through the actual air. Even waves on a rope, right? Or the slinkies. When we did the lab with the slinkies, that is a mechanical wave because you are actually vibrating the slinky. You are vibrating the medium. Now, it gets a little bit more challenging when we talk about the other type of wave because we are really vibrating the electromagnetic field, but we call those electromagnetic waves. So when you're actually vibrating the electromagnetic field in between, there's a little bit more that goes into it, and I'm using the term electromagnetic very loose because we haven't really talked about it yet. But we call these types of waves electromagnetic waves or EM waves, and we call these waves this because they fit on our electromagnetic spectrum. And you've probably already seen some of these terms before in your past sciences. I hope you have. Things like visible light, X-rays, UV rays, gamma rays. And these are all forms of electromagnetic radiation, electromagnetic waves. And so we have a little EM spectrum here. Hopefully this doesn't seem too new to you, but there are aspects of this spectrum that we can look at that you might not have realized in the past. So like first and foremost, one of the big things in terms of electromagnetic waves is that their energy is highly related to their frequency. And so which one of these waves is stronger, a gamma ray or a radio wave? Well, the gamma ray is definitely stronger. You definitely don't want to be hit by gamma rays. In fact, everything on the left side of this spectrum we protect ourselves from. Now, maybe you don't necessarily protect yourselves from gamma rays on a day-to-day basis, but that's because we already have something that protects us from it, and that's our atmosphere. It does a really good job of protecting ourselves from it already. X-rays, you go into a doctor's office, say you want to get an X-ray on your teeth. What do they put over your chest? Well, they put a really heavy vest, and what does that heavy vest have in it? Well, it has lead in it, and that lead stops the electromagnetic waves, the X-rays, from actually entering into your chest or into the areas where you have vital organs. UV rays, ultraviolet rays, well, what do we use to protect ourselves from that? Well, we use sunscreen in the summertime. These waves we don't really have to protect ourselves from because they don't have enough energy, what we would call ionizing energy, to actually ionize our cells or modify our cells to actually cause some damage. Now, the other big thing that I want to look at here is our wavelengths. So I'm going to skip really fast up just so that you remember this equation. Our v equals f lambda, velocity equals frequency times wavelength. This still applies to light waves, to electromagnetic waves. And in reality, all of these things are light rays. It's a little weird for students to understand at first, but infrared waves and microwaves and a blue light wave, well, there's nothing different between them other than their wavelength and their frequency. In fact, they act the same way. A microwave is really just light, but it's just light that we can't see. It is not a new type of wave. It is just the same type of wave, but one that we can't see. And so we classify it as a microwave. Now there's a small section of this spectrum that we can see, which we call the visible light spectrum. But if we look at our v equals f lambda equation, you could see that the shorter the wavelength, the higher the frequency, which makes sense because this v equals f lambda equation, f and lambda at a constant velocity have to be inversely related. As one goes up, the other has to go down in order to keep the same velocity. And so if you have very high frequency, you're going to have very short wavelength. If you have very long wavelength, you're going to have very low frequency. And so these waves, the lower frequency, have less energy, and these waves have higher energy. Higher energy, shorter wavelength. Alrighty? Remember that waves are traveling energy. They are not traveling matter. They are not translating any matter. They are just translating energy or transferring energy. So that is our EM spectrum. Remember, all of these are just light. There's nothing special about them other than the fact that we can't see it, right? Infrared is just red that is so far red that we can't see it, that our eyes can't pick up on it. In fact, we can only see a very small section of this EM spectrum. And so wanted to re-familiarize you with this formula because you are going to be using it this week. Just remember this thing right that I'm blocking is the biggest part here. All EM waves go through a vacuum at the exact same speed. We call this the speed of light, and it is 3 times 10 to the 8th meters per second. 3 times 10 to the 8th meters per second. We call this the speed of light. Notice when you are going in anything other than a vacuum, the light will inevitably slow down, and we'll talk about that in the future, how much it slows down, how that causes light to bend. But for right now, all EM light, all EM waves that go through a vacuum travel at the same speed. So all of these waves, gamma rays travel the same speed as microwaves in a vacuum, travel the same speed as ultraviolet rays in a vacuum. They're all the same speed, and that's 3 times 300 million meters per second. Speed of sound is a lot slower. We call this at STP, standard temperature and pressure, because sound waves can be altered by the pressure of the medium that they're going through and the temperature as well, and also the density. A lot of different things here, but it's 331 meters per second. So speed of light, 300 million meters per second. Speed of sound, 300 meters per second, roughly. So it's a huge, huge difference, right? This is the common thing of why do you see a lightning strike happen before you hear the thunder? Well, it's because that light is moving at 300 million meters per second, where sound is traveling at 300 meters per second. Much, 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 much slower. Okay? And that kind of brings us right back into what we saw last week. The red shift that we talked about last week, and the question that I asked you last week is, why don't we see an infinite amount of stars in the night sky? Well, when we have this red shift, things are moving away from us so far or so fast, or that the space in between us and them is quite literally expanding, quite literally becoming more space, well, that things become red shifted to the point where they are no longer red shifted, but they become actually infrared to the point where we actually might not even be able to pick up on them with our naked eye, and we might need an actual camera that can actually pick up this wavelength of light. And so there are stars out there, but sometimes they're actually just redshifted to the point where we can't see them, which is really, really interesting. Or can't see them with our naked eye, I should say. And so you're gonna be seeing a video on some other things in terms of radiation and what types of these radiations can affect humans. And so that's really it for this week. I'm gonna try and keep it as conceptual as possible. But other than that, see you later. Stay healthy. Wash your hands. And I'll talk to you next week.